What if the future has already happened? Not in the sense that it is predictable, but in the sense that it physically exists right now, as real and complete as the chair you're sitting in. The moment of your birth, the words you're hearing at this instant, the day you will die. According to one serious interpretation of modern physics, all of these exist together, equally and permanently, as fixed features of a structure that does not change. This idea is called the block universe. It is not science fiction, and it is not mysticism. It emerges directly from the mathematics of Albert Einstein's theory of relativity, the same theory that guides satellites, powers nuclear reactors, and has passed every experimental test thrown at it for more than a century. The block universe takes that established physics seriously and follows it to a conclusion most people find difficult to accept. Time does not flow. The present moment is not special. Past, present, and future are human categories, not features of reality. If that claim is correct, then your sense that time is passing, that this moment is happening and then slipping away, is something your brain constructs rather than something the universe actually does. The flow of time would be a kind of illusion, persistent and convincing, but an illusion nonetheless. Over the next stretch of this video, we will examine where this idea comes from, what evidence supports it, where it runs into trouble, and what it would mean if it were true. We begin not with speculation, but with a simple question that physicists have struggled to answer for generations. Does time really move? To understand why anyone would seriously propose that the future already exists, we have to start with something that feels so obvious it seems beyond question. Time passes. You can feel it. The morning becomes the afternoon. A cup of coffee cools on the desk. The child grows taller, the seasons turn, the old photographs yellow at the edges. Everything in ordinary experience tells us that time is a river, carrying us from a fixed past through a fleeting present toward an unknown future. This sensation is so deep that most languages are built around it. We speak of things that have happened, things that are happening, and things that will happen, and we treat these as fundamentally different states of being. For most of human history, this intuition was never seriously challenged, because there was no reason to challenge it. The flow of time was simply a given, a backdrop against which everything else occurred. When formal physics began to take shape in the 17th century, it inherited this assumption and built it into the foundation of the new science. The figure most responsible for that foundation was Isaac Newton, and the picture of time he established would dominate scientific thought for the next 200 years. Newton imagined time as something absolute. In his framework, time flowed uniformly and identically throughout the entire universe, completely independent of anything that happened within it. He described it as flowing equably, without relation to anything external. What this meant in practice was that there existed a single, universal clock ticking away in the background of reality. 1 second here was exactly 1 second everywhere, on Earth, on the Moon, in the empty space between distant stars. If you could somehow synchronize two clocks and then carry one to the far side of the galaxy, Newton's physics insisted they would still agree. Time was a master metronome, and every event in the cosmos marched to its beat. This was an extraordinarily powerful idea, not because it was poetic, but because it worked. Newton's laws of motion, combined with his law of universal gravitation, could predict the orbits of planets, the fall of an apple, the swing of a pendulum, and the timing of the tides with stunning accuracy. The assumption of absolute time was woven into all of it. When you calculate where a planet will be next year, you're assuming that the time on your clock and the time governing that planet's motion are one and the same. For everyday purposes, and even for most astronomical purposes, this assumption holds up remarkably well. It holds up so well that we still use Newtonian physics to send spacecraft across the solar system. Alongside absolute time, Newton placed absolute space. Just as there was one universal clock, there was one universal stage, a fixed and unchanging arena in which all events unfolded. Objects moved through this space, but the space itself was rigid and eternal. Together, absolute space and absolute time formed a kind of cosmic grid, a fixed framework of locations and moments against which any motion could be measured. An event happened at a particular place and at a particular time, and both of those values were objective facts that any observer anywhere would agree upon. The grid was the same for everyone. It is worth pausing to appreciate how natural this picture feels, because that naturalness is exactly what makes the later discoveries so jarring. Imagine a vast theatre. The stage is space, fixed and solid. The ticking of a single great clock backstage is time, the same for every seat in the house and every actor on the platform. Events are the actions that take place upon that stage, each one stamped with a definite location and a definite moment. Everyone watching agrees on the script, the timing, and the staging. There is one performance witnessed identically by all. This is the Newtonian universe, and for 2 centuries it appeared to be simply the way things were. Within this framework, the idea that time flows fit perfectly. There was a real, objective, present moment, the single instant at which the universal clock currently pointed. Everything before that instant was the past, fixed and gone. Everything after it was the future, not yet arrived. The present swept forward at a steady universal rate, the same for every observer in existence. Past, present, and future were not matters of perspective. They were built into the architecture of reality itself. The universe had a definite, shared now, and that now was advancing. But there was a quiet problem hiding inside Newton's system, one that troubled even Newton's contemporaries. It concerned the nature of gravity. In Newton's law, gravity acted instantaneously across any distance. If the sun were to suddenly vanish, the Earth would, according to the equations, fly off in a straight line at the very same instant, despite being 93 million miles away. The gravitational influence crossed that enormous gap with no delay whatsoever. This instantaneous action at a distance bothered many thinkers because it seemed to require that different parts of the universe communicate immediately, with infinite speed. Newton himself was uneasy about it. He could describe gravity with breathtaking precision, but he could not explain how it managed to act across empty space without any apparent mechanism and without any passage of time. For a long while, this discomfort remained in the background. The equations worked, and working equations tend to silence philosophical objections, but the assumption of instantaneous influence was deeply connected to the assumption of absolute time. If there is a single universal now, then it makes sense to speak of 2 distant events happening at the same instant, and it makes sense for gravity to act simultaneously across space. The whole structure depended on the existence of a shared, objective present that stretched across the entire cosmos. The trouble would arrive from an unexpected direction. It would come not from the study of gravity or planets, but from the study of light. Throughout the 19th century, physicists were steadily uncovering the nature of light, electricity, and magnetism, and the crowning achievement of that effort came from James Clerk Maxwell, who showed that light was an electromagnetic wave travelling through space at a specific fixed speed. That speed, roughly 186,000 miles per second, emerged directly from his equations. And here a strange feature appeared, one that did not fit comfortably with Newton's universe at all. Maxwell's equations specified the speed of light, but they did not specify what that speed was measured against. They gave a single number with no reference to who was doing the measuring or how fast they were moving. In a Newtonian world, this should not happen. Speeds are supposed to add together in a simple way. If you walk forward at 3 miles per hour along the aisle of a train moving at 50 miles per hour, then relative to the ground, you're moving at 53 miles per hour. Velocities combine by ordinary addition. So if light travels at a fixed speed, the obvious question is, fixed relative to what? Relative to its source? Relative to the fixed stage of absolute space? Physicists of the late 19th century assumed there must be some medium, which they called the ether, filling all of space and serving as the stationary backdrop against which light's true speed was defined. The Earth, they reasoned, must be moving through this ether, and that motion should be detectable. As the planet raced along its orbit, a beam of light sent in the direction of travel should behave differently from a beam sent across it, just as a swimmer moves at different speeds with and against a current. In the 1880s, 2 experimenters, Albert Michelson and Edward Morley, set out to measure this effect with extraordinary precision. They built an apparatus sensitive enough to detect the tiny differences that the Earth's motion through the ether should produce. They split a beam of light, sent the 2 halves along paths at right angles to each other, and recombined them to look for the expected mismatch in their timing. The experiment was careful, repeated, and refined, and it found nothing. No matter which direction they pointed their instrument, no matter the season or the Earth's position in its orbit, the speed of light came out exactly the same. There was no sign of the ether, no sign of any background medium, no detectable difference at all. This was a genuine crisis. The result seemed to say something impossible. The speed of light was the same regardless of how the measuring apparatus was moving. A beam of light approached you at the same speed whether you stood still or raced toward its source. This flatly contradicts the simple addition of velocities that governs everything in ordinary experience. Run toward an oncoming ball and it strikes you faster. Run toward an oncoming beam of light and it arrives at precisely the same speed as if you had stood perfectly still. Nature was insisting on something that the Newtonian framework declared could not be. For roughly 2 decades, physicists struggled to reconcile this result with the established picture. Some proposed clever fixes, suggesting that objects physically contracted as they moved through the ether in just the right way to hide its effects. These patches could be made to fit the numbers, but they felt arbitrary, like adjustments designed only to save a failing theory. The deeper meaning of the Michelson and Morley result remained obscure. The constancy of the speed of light sat in the middle of physics like a stone that no one could move and no one could explain. The resolution, when it finally came, did not patch the old framework. It demolished the most basic assumption underneath it. The reason the speed of light never changed, one young physicist would argue, was not that the ether contracted objects, and not that the measurements were flawed. The reason was that time and space themselves were not what Newton had believed. The universal clock did not exist, the fixed stage did not exist, and the price of accepting that the speed of light is truly constant for everyone would be the surrender of absolute time itself. To keep light's speed fixed, something else had to bend. The question was what? The answer came in 1905 from a 26-year-old patent clerk in Bern, Switzerland, who had been unable to secure an academic position and was examining applications for electrical devices while turning over the deepest problems in physics in his spare time. Albert Einstein approached the puzzle of light's constant speed in a way that almost no one else had been willing to consider. Everyone else had treated the constancy of light speed as a problem to be explained away, a stubborn fact that must somehow be reconciled with the obvious truths of absolute space and time. Einstein did the opposite. He took the constancy of light as a starting principle, something to be accepted as fundamentally true, and then asked what the rest of physics would have to look like in order to accommodate it. If the speed of a light truly is the same for every observer, he reasoned, then it is not light that needs explaining. It is our assumptions about time and space that need to change. He built his theory, which came to be called special relativity, on 2 simple postulates. The first was that the laws of physics are the same for all observers moving at constant velocity. There is no privileged vantage point, no observer who can claim to be truly at rest while everyone else moves. If you are sealed inside a smoothly moving train with no windows, no experiment you perform inside the train can tell you whether you are moving or standing still. Motion at a steady speed is only ever relative to something else. This idea was not entirely new. A version of it traced back to Galileo. The second postulate was the radical one. The speed of light in empty space is the same for all observers, regardless of their motion or the motion of the light's source. This was simply taking the Michelson and Morley result at face value and refusing to flinch. Each postulate on its own seems reasonable enough. The shock comes from holding both at the same time, because together they cannot coexist with the idea of universal absolute time. Einstein saw this with remarkable clarity, and he followed the logic wherever it led, even when it led somewhere that defied all common sense. To see why, consider what it actually means for the speed of light to be constant for everyone. Speed is distance divided by time. It is a measurement that combines how far something travels with how long the journey takes. If 2 observers moving differently both measure the same beam of light and both get exactly the same speed, but they are moving at different velocities relative to each other, then something has to give. They cannot agree on both the distance and the time. If the ratio of distance to time must come out identical for both of them despite their different motion, then their measurements of distance and their measurements of time must themselves differ. In other words, to keep the speed of light fixed, space and time have to flex. Einstein worked out exactly how they must flex, and the consequences were precise and quantifiable. The first consequence is that moving clocks run slow. If you watch a clock that is moving rapidly relative to you, you will observe it ticking more slowly than your own. This is not a mechanical defect in the clock, and not an illusion of perception. Time itself, as measured along that moving clock's path, genuinely passes at a different rate. The effect is called time dilation. At everyday speeds, it is far too small to notice, which is why it escaped detection for so long. But as an object approaches the speed of light, the effect grows dramatic. A clock moving at 90% of light speed ticks at less than half the rate of a stationary one. Push closer to light speed, and the moving clock nearly freezes from the stationary observer's point of view. The second consequence is that moving objects contract along their direction of motion. A rod flying past you at high speed is genuinely shorter, measured in your frame of reference, than the same rod at rest. Space itself compresses. The third consequence ties these together with mass and energy, eventually yielding the most famous equation in all of science, the statement that energy and mass are two expressions of the same underlying quantity. But for our purposes, the crucial consequence is the one Einstein identified as the true heart of the revolution. It concerns simultaneity, the question of whether two separate events happen at the same time. In Newton's universe, simultaneity was absolute. Two events either happened at the same moment or they did not, and every observer in the cosmos would agree on the answer because there was a single universal clock against which all events were timed. Einstein showed that this is false. Whether two separated events are simultaneous depends on the motion of the observer. Two events that one observer judges to happen at the same instant will be judged by another observer, moving differently, to happen at different times, one before the other. And neither observer is mistaken. There is no universal clock to consult, no master timing that would settle the dispute. Each observer's judgment of simultaneity is equally valid. The very notion of the same time at two different places loses the absolute meaning Newton gave it. This is the relativity of simultaneity, and it is the conceptual hinge on which everything else turns, so it is worth making concrete. Einstein himself reached for an example involving a train, and the example remains the clearest way to see the effect. Imagine a very long train moving down a track at enormous speed, and imagine an observer standing on the embankment beside the track, watching it pass. Now suppose two bolts of lightning strike the train, one at the front and one at the rear, and suppose they strike in such a way that the observer on the embankment standing exactly midway between the two strike points sees the two flashes arrive at the very same instant. For this observer, the conclusion is simple. The light from each strike travelled the same distance to reach the eye, and both flashes arrived together, so the two strikes must have happened simultaneously. Now consider a second observer, seated exactly in the middle of the train, moving along with it. At the moment the lightning strikes, this passenger happens to be lined up with the observer on the embankment. But the passenger is moving. During the tiny interval that the light takes to travel from the strike points toward the middle of the train, the passenger has moved forward, toward the flash at the front and away from the flash at the rear. As a result, the light from the front strike reaches the passenger slightly earlier, and the light from the rear strike reaches the passenger slightly later. Since the speed of light is the same in every direction for the passenger, just as the second postulate demands, the passenger can only draw one conclusion. The lightning struck the front of the train before it struck the rear. The two strikes were not simultaneous at all. Here is the essential point. The embankment observer says the strikes were simultaneous. The train passenger says the front strike happened first. Both are correct. There is no experiment, no measurement, no higher authority that can declare one of them right and the other wrong, because the constancy of the speed of light forbids any privileged frame of reference. Simultaneity is not a feature of the events themselves. It is a relationship that depends on the motion of whoever is observing. Two events that are simultaneous in one frame of reference are not simultaneous in another. The order of events separated in space can flip depending on how fast you're moving. Take a moment to sit with how strange this is, because its implications run deep. We are not talking about a delay caused by the time light takes to reach the eye, which everyone already knew about and could correct for. The embankment observer has already accounted for travel time and concluded that the strikes were genuinely simultaneous. The disagreement is about the actual timing of the events, after all such corrections are made. It is built into the structure of space and time. The phrase "at the same time," which seems so clear and so absolute, turns out to have no universal meaning. It only has meaning relative to a particular state of motion. Now we can begin to see the first cracks in the flowing river of time. If different observers genuinely disagree about which events happen at the same moment, then there is no single, shared present moment that everyone in the universe occupies together. My now and your now are not the same now if we are moving relative to each other. The set of events that I consider to be happening right now, all across the universe, is different from the set of events that you consider to be happening right now. And if there is no universal present, then the whole picture of a single moving now, sweeping forward through time and dividing a fixed past from an open future, starts to fall apart. Whose now would be doing the moving? This is not philosophy imposed on top of the physics. It comes straight out of the physics itself, from two modest-sounding postulates and the unforgiving logic that connects them. Einstein did not set out to abolish the universal present. He set out to explain why light always travels at the same speed, but the explanation, followed honestly, dissolved the foundation on which the flowing river of time had always rested. The constancy of light's speed and the absolute simultaneity of distant events simply cannot both be true. One of them had to go, and the experiments had spoken clearly about light. Yet special relativity, as Einstein first presented it in 1905, still felt like a theory about measurements, about what different observers see and record. It described how clocks slow and rulers shrink and simultaneity shifts, but it did not yet offer a single, unified picture of what reality fundamentally is. The equations contained that picture, but it was hidden in the algebra, waiting for someone to recognize the deeper geometric structure underneath. The person who would see it was not Einstein himself, but one of his former teachers, a mathematician who had once dismissed the young Einstein as a lazy student. He would take Einstein's equations and reveal that they were describing something far more profound than a set of rules about moving clocks. They were describing the architecture of a single, four-dimensional reality. And in that architecture, the seeds of the block universe were already present, waiting to be named. The mathematician was Hermann Minkowski, and in 1908, 3 years after Einstein's paper appeared, he delivered a lecture that opened with a striking declaration. The views of space and time that he wished to present, he announced, had sprung from experimental physics, and therein lay their strength. From this point forward, he said, space by itself and time by itself were doomed to fade into mere shadows, and only a kind of union of the two would preserve an independent reality. What Minkowski had recognized was that Einstein's equations, with all their talk of slowing clocks and contracting rulers, were most naturally understood not as statements about how measurements change, but as statements about the geometry of a single, unified entity that fused space and time together. He gave that entity a name. He called it Spacetime. To grasp what Minkowski meant, we need to think carefully about what an event actually is. In physics, an event is not a dramatic occurrence. It is simply a point with a definite location and a definite time. A firecracker going off, 2 billiard balls colliding, a photon striking a detector, your finger touching a screen at a particular instant. Each of these is an event, and to specify it completely, you need 4 numbers, 3 of them located in space, telling you how far along, how far across, and how far up it sits, relative to some reference point. The 4th number locates it in time, telling you when it happens. 3 numbers for space, 1 for time, 4 numbers in total. Every event in the history of the universe can be pinned down by exactly 4 such numbers. Minkowski's insight was to treat these 4 numbers as coordinates in a single 4-dimensional space. Just as a point on a flat map requires 2 numbers, and a point in a room requires 3, a point in space-time requires 4. We cannot visualize 4 dimensions directly. Our minds and our eyes are built for 3. But mathematically there is no obstacle whatsoever to working in 4 dimensions, or in any number of dimensions. The mathematics of 4-dimensional geometry is just as rigorous and just as consistent as the geometry of an ordinary cube. And when Einstein's equations are rewritten in the language of this 4-dimensional geometry, something remarkable happens. The strange effects of special relativity, the slowing clocks and shrinking rulers and shifting simultaneity, all become natural and almost inevitable features of a single geometric structure. They stop looking like a collection of peculiar rules and start looking like different perspectives on one underlying object. Here is a way to build the intuition gradually. Imagine you want to describe the history of a single particle, say a speck of dust drifting through empty space. In ordinary thinking, you would say the particle is at one location now, a slightly different location a moment later, another location after that, and so on, tracing a path through space as time passes. But Minkowski invites you to think differently. Instead of imagining the particle moving through space as time flows, picture the entire history of the particle laid out at once, as a continuous line threading through the four-dimensional block of space-time. Each point on that line represents the particle being at a particular place at a particular time. The line as a whole captures the particle's complete existence, from beginning to end, as a single static object. This line is called the particle's world line. Your own world line is the complete four-dimensional trace of your existence. It begins at the event of your birth, a particular place at a particular time, and it ends at the event of your death, another place at another time. In between, it winds through space-time, recording every location you ever occupy at every moment you occupy it. Every step you take, every breath, every heartbeat is a point along this world line. From the four-dimensional perspective, you're not a three-dimensional object that moves and changes as time passes. You're a four-dimensional object, long and thin, stretched out along the time direction, with the shape of your entire life frozen into the geometry. The you of this morning and the you of tonight are different cross-sections of the same extended object, like different slices of a loaf of bread. This shift in perspective is subtle but enormous, and it deserves careful attention, because it is the bridge that carries us from the equations of relativity to the block universe itself. In the ordinary view, there is a three-dimensional world, and this world changes from moment to moment as time flows. The present is real, the past has ceased to exist, and the future does not yet exist. In Minkowski's view, there is a four-dimensional structure, and this structure simply is. It does not change, because change means being different at different times, and the whole of time is already included within the structure. There is no flowing now sweeping through it. Every moment is just a location along the time dimension, no more special and no more privileged than any particular location along a spatial dimension. The structure exists as a complete whole, all moments together. Consider an analogy with an ordinary map because it captures the essential reframing. On a map of a country, every city exists simultaneously as a point on the page. The map does not show one city existing now, while another waits to come into being. Boston and Los Angeles are both simply there, at their respective coordinates, coexisting on the same sheet of paper. The distance between them is a fixed geometric fact. Now imagine that one of the directions on this map, instead of representing north and south or east and west, represented time. Then the events of yesterday and the events of tomorrow would coexist on the map exactly as Boston and Los Angeles do, each at its own coordinate, all equally real, all simply present in the structure. The block universe is this idea taken with full seriousness. Space-time is the map, and every event that has ever happened or will ever happen occupies its fixed position within it. The reason this picture follows so naturally from relativity, rather than being an arbitrary philosophical overlay, comes back to the relativity of simultaneity. Recall that different observers, moving differently, disagree about which events are happening at the same time. In the language of space-time, this disagreement has a clean geometric meaning. When you select all the events that you consider to be happening right now, all across the universe, you're effectively taking a slice through the four-dimensional block, cutting it along a particular angle to produce a three-dimensional snapshot of the present moment. This slice is sometimes called a surface of simultaneity. It is your now, spread across all of space. But here is the crucial point. An observer moving relative to you slices the block at a different angle. Their now is a different slice, tilted with respect to yours. This is where the existence of the whole block becomes almost unavoidable. Picture a loaf of bread, and picture two bakers who disagree about how to slice it. One cuts straight down, producing vertical slices. The other cuts at a slant, producing slices tilted at an angle. The two bakers carved the loaf into different sets of slices, but they are slicing the same loaf. The bread as a whole exists independently of how anyone chooses to cut it. Now apply this to space-time. Different observers carve the four-dimensional block into different stacks of present moments, tilted relative to one another. But for these different slicings to all be valid, all describing the same reality, the entire loaf, the whole block of space-time, must exist. An event that lies in my future, beyond my current slice, may lie in the present slice of an observer moving differently from me. If that event is real and present for them, and we are describing the same reality, then in what sense can it be unreal and non-existent for me? This argument has a formal name. It is sometimes called the Reitdijk-Putnam argument, after two philosophers who developed it independently, and it runs as follows. Take any event that lies in your future. It is possible, in principle, to find some observer moving at some velocity relative to you, who is passing through your location right now, but whose surface of simultaneity, whose now includes that future event. For that observer, the event is happening in the present, but the two of you are at the same place at the same moment, sharing the same point of space-time. If the present moment is what is real, and that observer's present includes an event that lies in your future, then that future event must be just as real as anything in your own present. By stitching together the present moments of many observers, all passing through your location at different velocities, you can establish that events throughout your future and throughout your past are all equally real. The conclusion is that the distinction between past, present, and future has no objective standing. All events, whenever they occur, exist on the same footing. It is important to be precise about what this argument does and does not claim, because it is easy to overstate. It does not claim that you can see the future, or send signals to it, or learn what it contains before it arrives in your own experience. The speed of a light still strictly limits what can influence what, and we will return to that limit, because it is essential. The argument is about existence, not access. It says that the events of the future are real features of the space-time structure, fixed and present in the four-dimensional block, even though you cannot reach them or know them in advance from your particular location along your world line. Your ignorance of the future is real. What the argument denies is that this ignorance corresponds to the future being genuinely open or non-existent. The future is settled. You simply have not arrived at your knowledge of it yet. By now, the shape of the block universe stands fairly clear. Reality is a four-dimensional structure containing all events, past, present, and future, as fixed and equally real features. The passage of time, the sense of a moving present, is not part of this structure. It is something else, something that requires a separate explanation, because the physics itself contains no flowing now. And yet this raises an immediate and pressing question. If the block is right, if all moments coexist and nothing genuinely flows, then why does it feel so overwhelmingly as though time passes? Why do we remember the past and not the future? Why does the present feel so vividly real while the future feels merely possible? The geometry of Minkowski's spacetime makes a bold claim about the nature of reality, but it leaves our most basic experience of time entirely unexplained. To take the block universe seriously, we have to confront that gap directly, and we have to ask what, if anything, picks out the present moment as special. The search for a special present moment somewhere in the laws of physics has consistently come up empty, and this absence is one of the strongest pieces of evidence for the block universe. To appreciate why, it helps to look closely at what the fundamental equations of physics actually say about time, because the answer is surprising. When physicists write down the laws that govern how the universe behaves, from Newton's mechanics to Einstein's relativity to the equations of quantum theory, time appears in those laws as a variable, a coordinate, a quantity that can take any value. What does not appear anywhere in these laws is a marker indicating which value of time is now. The equations describe how things at one time relate to things at another time, but they contain nothing that singles out a particular moment as the privileged present. Think about what this means. Imagine handing the complete laws of physics to someone who knew nothing about the flow of time. They could use those laws to calculate the state of the universe at any moment, given its state at any other moment. They could run the calculation forward to find the future or backward to find the past with equal ease, but nowhere in the equations would they find any instruction telling them where the present is located, which moment is happening right now. The laws treat all moments alike. They describe a structure, the relationships between events across all of time, without ever pointing to one moment and saying this one is real and the others are not. The now is simply not there in the physics. It has to be added by hand, imposed from outside if it is to be there at all. This is genuinely strange when you consider how central the present moment feels to our experience. Nothing seems more obviously real than the present. The past is gone, a collection of memories. The future is unknown, a realm of possibility. Only the present is actually happening, actually here. And yet when we examine the laws that govern the physical world with the greatest precision we have ever achieved, the present moment is nowhere to be found. The physics describes a universe of events related to one another, but it does not describe a universe with a moving spotlight of nowness sweeping through it. If the present were a fundamental feature of reality, you might expect it to show up somewhere in the fundamental description of reality. It does not. Some have tried to argue that this absence merely reflects a limitation of current physics, that we simply have not yet discovered the law that picks out the present. But the difficulty runs deeper than a missing equation. Relativity does not just fail to identify a universal present, it positively forbids one. We have already seen why. Because simultaneity is relative, because observers in different states of motion slice space-time into different sets of present moments, there cannot be a single objective now shared by the whole universe. Any attempt to define the present moment must pick a particular frame of reference, a particular way of slicing the block, and relativity insists that no frame is privileged over any other. To declare one slicing the true present would be to violate the core principle that the laws of physics look the same in every frame. The relativity of simultaneity does not merely leave the present undefined, it makes a universal present incompatible with the structure of space-time. This creates a deep tension between physics and experience, and that tension sits at the very heart of the block universe debate. On one side stands our immediate overwhelming experience of a flowing present, and now that is vividly real and constantly advancing, dividing a settled past from an open future. On the other side stands the physics, which finds no present moment in its equations, and forbids any universal one in its geometry. These two pictures could hardly be more opposed. One of them must be giving way. Either our experience is revealing something real that the physics has somehow missed, or the physics is revealing something real, and our experience is, in some sense, misleading us about the nature of time. The philosopher and mathematician Hermann Weyl captured the block universe resolution of this tension in a now famous image. He suggested that the objective world simply is, it does not happen. There is no flow, no becoming, no genuine passage. What happens, he proposed, is only that our consciousness crawls along our world line, and the events along that world line come to life for us one after another as we encounter them. The events themselves do not come into being and pass away. They are all there, permanently, in the block. It is only our awareness that moves through them, like a reader's eye moving across a page where all the words are already printed. The sense of time passing, in this view, is a feature of how consciousness traverses the structure, not a feature of the structure itself. This is a radical reframing of the most basic feature of experience, and it naturally provokes resistance. Surely one wants to object. The passage of time is not an illusion. I can feel it. I watch the present become the past. I anticipate a future that has not yet happened. How can all of this be a kind of trick of the mind? But it is worth remembering that physics has overturned powerful intuitions before, repeatedly, and that the feeling of obviousness is not a reliable guide to truth. It once seemed obvious that the Earth was stationary and the heavens revolved around it. Nothing in ordinary experience suggests that the ground beneath your feet is hurtling through space at enormous speed, both spinning and orbiting. And yet it is. The stillness of the Earth is a compelling illusion produced by the fact that we move along with it. Perhaps the flow of time is a similar illusion, compelling precisely because we are embedded within it and cannot step outside to see the structure whole. There is a useful comparison to be drawn here with the way we already understand space. Consider the word here. When you say something is here, you mean it is at your location, but you understand perfectly well that here is not an objective feature of the universe. Your here is someone else's there. There is no cosmically privileged location that counts as the real here for everyone. Here simply marks wherever the speaker happens to be standing. Locations in space do not come in two kinds, the special here and the lesser elsewhere. They are all on equal footing, and here is just a label that points to wherever you are. The block universe proposes that now works exactly the same way. Now is not an objective feature of the universe, it simply marks wherever along the time dimension you happen to be located. Your now is someone else's then. There is no cosmically privileged moment that counts as the real present for everyone. Moments in time, like locations in space, are all on equal footing, and now is just a label that points to wherever along your world line your awareness currently sits. If you accept the parallel between space and time that relativity so strongly suggests, this conclusion follows with a certain inevitability. We do not believe that distant places blink out of existence simply because we are not there. The far side of the world exists right now, fully real, even though you're not present to experience it. The block universe asks only that you extend the same reasoning to time. Distant moments do not blink out of existence simply because you're not there to experience them. Yesterday exists at its location in time, fully real, even though you are not present there. Tomorrow exists at its location in time, fully real, even though you have not yet arrived. The reluctance to accept this is, in the block universe view, simply a prejudice rooted in the particular way conscious beings experience time, a prejudice that the physics gives us reason to set aside. And yet the matter cannot be settled so easily, because the difference between space and time is not merely a matter of prejudice. There are real, physical asymmetries between them that any honest account must confront. You can move freely through space, forward and back, left and right, returning to where you started. You cannot move freely through time. Your world line threads through the block in one direction only, from past toward future, never doubling back. You remember the past, but not the future. Causes precede their effects, never the reverse. Eggs break, but do not unbreak. These asymmetries are real and measurable, and they seem to mark a profound difference between the time direction and the space directions of the block. If time is truly just another dimension, no different in principle from the spatial ones, why does it behave so differently in these respects? Why does the block have a grain to it? A direction along which things run that they never run backward? The block universe by itself does not answer this. The four-dimensional structure is the same whether you read it from past to future or from future to past. The geometry contains no arrow. And so, the defender of the block faces a genuine challenge. If reality is a static four-dimensional structure, with no flowing time and no privileged present, then the obvious directionality of our experience, the relentless one-way character of time, must come from somewhere. It must be a feature not of the fundamental geometry, but of the particular contents of the block, the way matter and energy are arranged within it. This points toward one of the deepest ideas in all of physics, a concept that may hold the key to why we experience time as flowing in one direction even if, at the deepest level, it does not flow at all. That concept is entropy, and to understand the arrow of time, we have to understand why disorder so relentlessly increases. Entropy is, at its simplest, a measure of disorder, but that plain definition conceals an idea of extraordinary depth and reach, one that connects the breaking of an egg to the death of stars and may explain why we experience time as flowing at all. To understand entropy, begin with a concrete and familiar scene. Picture a glass containing a few cubes of ice floating in warm water. Leave it on the table and come back later. The ice has melted, and the water has settled to a uniform, lukewarm temperature. You have watched this happen countless times, and you have never once seen the reverse. You have never returned to a glass of lukewarm water and found that ice cubes had spontaneously formed within it while the surrounding water grew warmer. The melting happens. The unmelting never does. This one-way character is so reliable that it amounts to a law, and the law concerns entropy. The reason the ice melts, and never unmelts, comes down to counting, specifically counting the number of ways the molecules can be arranged. When the ice is frozen, its water molecules are locked into a rigid, orderly crystal lattice, each one held in a particular position. There are relatively few ways to arrange molecules into that kind of organized structure. When the ice melts and the molecules spread evenly through the warm water, jostling freely, there are vastly, astronomically more ways for them to be arranged while still producing the same overall lukewarm glass of water. Entropy is essentially a count of how many microscopic arrangements correspond to a given large-scale situation. A state of low entropy, like the ice, can be realized in only a few ways. A state of high entropy, like the uniform water, can be realized in an overwhelming number of ways. Now, the crucial insight. The molecules in the glass are constantly moving and rearranging, sampling different configurations at random. Because there are so many more high-entropy arrangements than low-entropy ones, the system is overwhelmingly likely to find itself in a high entropy state simply because those states are so much more numerous. It is like shuffling an enormous deck of cards. A shuffled deck is almost never in perfect numerical order, not because order is forbidden, but because out of the staggering number of possible orderings, only a tiny handful count as ordered, while essentially all the rest count as disordered. Shuffle the deck and you will, with overwhelming probability, get a disordered result, because disordered results vastly outnumber ordered ones. The same logic governs the molecules. Disorder wins not because of any force pushing toward it, but because disorder is simply far more probable. This is the second law of thermodynamics. The total entropy of an isolated system tends to increase over time, marching from less probable, more ordered states toward more probable, more disordered ones. Here is what makes entropy so important for our story. The second law of thermodynamics is the only fundamental law in all of physics that distinguishes the past from the future. Every other basic law works equally well in both directions of time. If you watched a video of two billiard balls colliding and bouncing apart, you could not tell whether the film was running forward or backward, because both versions obey the laws of motion perfectly. Run the collision in reverse, and it is still a valid collision. The same is true of planets orbiting, of light propagating, of nearly every fundamental process when examined in isolation. The microscopic laws of physics are, with one subtle and minor exception we can set aside, completely symmetric in time. They do not care which way time runs, they contain no arrow. But entropy does contain an arrow. Entropy increases toward the future and decreases toward the past. This single fact, the relentless increase of entropy in one direction, may be the entire physical basis for the difference between past and future. The melting ice, the cooling coffee, the breaking egg, the aging body, the building that crumbles but never spontaneously assembles itself from rubble, all of these are manifestations of entropy increasing. They all run one way, and because they all run the same way, they collectively define a direction in time, a distinction between earlier and later. This is what physicists call the arrow of time. It does not come from the fundamental laws which are blind to time's direction. It comes from entropy, from the overwhelming statistical tendency of disorder to increase. This gives the defender of the block universe a powerful resource. Recall the challenge. If reality is a static four-dimensional structure with no genuine flow, why does time seem so insistently directional? The answer entropy provides is that the directionality is real, but it is a property of how matter is arranged within the block, not a property of any flowing now. The block does not flow, but it does have a grain. Along the time direction, entropy is low at one end and high at the other. The structure is lopsided in its contents, even though it is static in its existence. The arrow of time is this lopsidedness. It is built into the distribution of order and disorder across the block, like the grain in a piece of wood that runs along its length without the wood itself moving. And this connects directly to why we remember the past but not the future, which might be the most personally compelling asymmetry of all. Memory is a physical process. To form a memory is to create a record, an ordered trace in the brain, or in a photograph, or in the rings of a tree, or in any physical system that preserves information about an earlier state. Creating and maintaining such records depends on entropy. A record is a kind of order, and the formation of order in one place is always paid for by a greater increase of disorder elsewhere, exactly as the second law requires. The reason we can have records of the past but not of the future is bound up with the fact that entropy was lower in the past. The low entropy past leaves traces in the higher entropy present. The future, being higher in entropy still, leaves no such traces reaching back to us. We remember the direction of lower entropy. We are ignorant of the direction of higher entropy. Memory itself has an arrow because entropy has an arrow. But this answer, satisfying as it is, immediately raises a far deeper and more unsettling question, one that pushes the explanation back to the very origin of the universe. If entropy is always increasing, if disorder relentlessly grows as we move toward the future, then it must have been lower in the past, and lower still further back. Following this chain to its logical end, the entropy of the universe must have been extraordinarily, almost inconceivably low at the very beginning, at the moment of the Big Bang. The early universe must have been in a state of staggeringly high order, an enormously improbable configuration, in order for entropy to have been climbing ever since. This is sometimes called the past hypothesis, the proposal that the universe began in a special state of very low entropy, and that everything we call the arrow of time ultimately traces back to that initial condition. The difficulty is explaining why the universe began in such an improbable state. If high entropy states are overwhelmingly more numerous, and therefore overwhelmingly more probable, then a low entropy beginning is exactly the kind of state we should least expect the universe to have started in. It is as though the cosmos was dealt a perfectly ordered deck at the start against staggering odds, and has been shuffling toward disorder ever since. Why the universe was born in such a finely ordered condition remains one of the genuinely unsolved problems in physics. Various proposals exist involving the dynamics of cosmic inflation, or the structure of gravity, or the idea that our universe is one region within a far larger structure where entropy behaves differently in different places, but none of these is established. The low entropy beginning is observed, woven into everything we see, yet not fully explained. What matters for our purposes is the relationship this reveals between entropy and the block universe, because it changes the character of the whole picture. The arrow of time, the thing that makes the future feel so different from the past, turns out not to be a feature of time flowing. It is a feature of how the contents of the universe are arranged, with order concentrated at one temporal end and disorder spreading toward the other. In the block universe, this arrangement is simply a static fact about the four-dimensional structure. The block contains a region of very low entropy, which we call the early universe, and entropy rises smoothly as you move along the time direction away from that region. We find ourselves embedded in this gradient, and the direction of increasing entropy is what we experience as the forward direction of time. The flow we seem to feel is, in this account, our awareness moving through a structure whose contents are arranged with a definite grain. So the block universe can accommodate the arrow of time. It does not need a flowing present to explain why time seems directional. It needs only the lopsided distribution of entropy, anchored in that mysterious low entropy beginning. The directionality is real, measurable and pervasive, but it is a property of the contents, not of any cosmic flow. This is an elegant resolution, and for many physicists it is persuasive, and yet it leaves a residue of unanswered questions that we cannot ignore. The arrow of time explains why we move from past to future rather than the reverse, but it does not by itself explain the vivid sense that we are moving at all, the feeling of the present continuously becoming. Entropy gives the block a direction. It does not obviously give the block a flow. Whether anything does, or whether the flow is purely a construction of the conscious mind, remains open. And before we can address that, we have to confront an even sharper challenge to the whole tidy picture, a challenge that comes from the one domain of physics we have so far set carefully aside. The smooth, deterministic, fully laid out block of relativity meets a serious rival in the strange and probabilistic world of the quantum, where the future may not be written after all. Quantum mechanics is the most successful physical theory ever devised, confirmed to extraordinary precision in every experiment designed to test it, and it presents the block universe with its most serious difficulty. The problem is not a minor technical wrinkle, it strikes at the central claim. The block universe, as it emerges from relativity, depicts a reality in which every event is fixed, definite, and equally real, the future as settled as the past. Quantum mechanics, in its standard formulation, appears to describe a reality in which the future is genuinely open, in which events are not fixed until they happen, in which probability and indeterminacy lie at the foundation of things. These two pictures pull in opposite directions, and reconciling them is one of the great unfinished tasks of physics. To see the tension clearly, we need to understand what quantum mechanics actually says about the state of a physical system, because it is radically different from anything in classical physics. In the everyday world and in Newton's physics, an object has definite properties at all times. A ball has a definite position and a definite velocity, whether or not anyone is looking. You might not know these values, but they exist, sharp and determinate. Quantum mechanics overturns this. According to the theory, a particle such as an electron does not, in general, possess a definite position before it is measured. Instead, it exists in what is called a superposition, a kind of blended combination of many possible positions at once. The electron is not secretly at one location that we simply have not discovered. The mathematics insist that, in a meaningful physical sense, it occupies a spread of possibilities simultaneously, none of them singled out as the real one. This is not loose metaphor or a confession of ignorance. The superposition has measurable physical consequences that distinguish it sharply from mere uncertainty about a hidden value. The most famous demonstration is the double-slit experiment, which reveals the strange nature of quantum reality with stark clarity. Send a beam of electrons one at a time toward a barrier with two narrow slits cut in it, and let them strike a detecting screen behind. Common sense says each electron must pass through one slit or the other, and the pattern building up on the screen should be the simple sum of two groups, one behind each slit. That is not what happens. Instead, the electrons build up an interference pattern, a series of alternating bands, exactly the pattern you would get if each electron had passed through both slits at once and interfered with itself like a wave. Even though the electrons arrive one at a time, as individual particles, the pattern that accumulates can only be explained if each electron traversed both paths simultaneously, in superposition, before striking the screen. Now comes the part that bears directly on the block universe. When you actually measure which slit the electron goes through, by placing a detector at the slits, the interference pattern vanishes. The act of measurement forces the electron to take a definite path, to be at one slit or the other, and the wave-like behavior disappears. This transition, from a spread-out superposition of many possibilities to a single definite outcome, is called the collapse of the wave function. Before measurement, the electron is described by a wave of possibilities, each with a certain probability. After measurement, there is a single actual result, and the other possibilities have vanished. The theory predicts the probabilities of the various outcomes with perfect accuracy, but it does not predict which particular outcome will occur on any given measurement. That appears to be genuinely random, undetermined until the moment of measurement. Consider how directly this collides with the block universe. In the block, every event is already there, fixed in the four-dimensional structure. The result of any future measurement is, on that view, simply a feature of the block, settled in advance, waiting at its location along your world line. But quantum mechanics, read straightforwardly, says the result of a measurement does not exist until the measurement is made. It is not that we are ignorant of a predetermined outcome. It is that before the measurement, there is no determinate outcome to be ignorant of. The future in this reading is not a fixed region of an existing block. It is a realm of genuine possibility, crystallizing into actuality only as measurements occur. If that is correct, then the future is not already there. It is being made moment by moment as the wave function collapses and possibilities become facts. This is a profound conflict, and physicists and philosophers have wrestled with it for the better part of a century without reaching consensus. The disagreement centers on what quantum mechanics is really telling us about reality, a question known as the interpretation of quantum mechanics. The mathematics of the theory is not in dispute. Everyone agrees on how to calculate the probabilities, and the calculations work flawlessly. What remains fiercely contested is what the mathematics means, what kind of world it describes, and the various interpretations differ precisely on the points that matter most for the block universe, on whether collapse is a real physical process, on whether the future is open or fixed, on whether randomness is fundamental or only apparent. One major interpretation, often associated with the early founders of quantum theory and called the Copenhagen interpretation, takes the collapse of the wave function as a real and irreducible feature of nature. On this view, before measurement there genuinely is no definite outcome, only a spread of possibilities, and the act of measurement genuinely produces a definite result out of that spread. The randomness is fundamental. The future is genuinely open. If this interpretation is correct, the smooth, fully determined block universe of relativity seems to be in serious trouble, because reality would contain irreducible chance, and the future would not be fixed but actively generated as measurements unfold. The block would, at best, be partial, with a settled past and a present edge where possibilities are still resolving into fact. But the Copenhagen interpretation is not the only option, and some of the alternatives restore the block universe in striking ways. The most dramatic is the many worlds interpretation. This view takes the mathematics of quantum mechanics at face value and removes the collapse of the wave function entirely. According to many worlds, the wave function never collapses. Instead, all the possibilities contained in a superposition are equally real, and they all happen. When you measure an electron that was in a superposition of two positions, the universe does not select one outcome and discard the other. Rather, the universe splits, or more precisely branches, into multiple versions, one for each possible outcome. In one branch, the electron was found here, and there is a version of you who recorded that result. In another branch, the electron was found there, and a different version of you recorded the alternative. Both branches are equally real. Both versions of you are equally real. They simply no longer interact. What makes many worlds so significant for our discussion is that it eliminates the randomness and the collapse that conflicted with the block universe. In the many worlds picture, nothing is undetermined. Everything that can happen does happen in one branch or another. The wave function evolves smoothly and deterministically for all time, with no collapse and no chance. The apparent randomness you experience is simply the result of not knowing which branch you will find yourself in. But every branch exists, every outcome is realized, and the whole vast structure of branching possibilities is fixed and complete. This is in effect a block universe, but an immensely larger and more intricate one than relativity alone suggested. It is a block that contains not a single history, but a continuously branching tree of all possible histories, every one of them equally real, all coexisting in a structure that, taken as a whole, is just as fixed and determined as the simple block of relativity. The future is settled, not because only one thing will happen, but because everything will. There are still other interpretations that bear on the question in different ways. The de Broglie-Bohm theory, also called pilot wave theory, restores determinism by proposing that particles always have definite positions after all, guided by a real physical wave, with the apparent randomness reflecting only our ignorance of the precise initial conditions. On this view, the future is fully determined, and a block universe is entirely natural, though the theory has its own difficulties reconciling with relativity. Other approaches, called retrocausal interpretations, take an even more striking position. They propose that influences in the quantum world can run backward in time as well as forward, so that a measurement now can affect the state of a particle in the past. These interpretations fit remarkably naturally with the block universe, because in a structure where past and future coexist on equal footing, there is no special reason that influence should run only one way. If all of time is laid out together, a connection between a later event and an earlier one is no more mysterious than a connection running the usual direction. The honest situation is this: quantum mechanics, in its bare mathematics, does not by itself settle whether the future is open or fixed. The answer depends entirely on which interpretation correctly describes reality, and that question remains unresolved. Some interpretations, like Copenhagen with real collapse, threaten the block universe and suggest a genuinely open future. Others, like many worlds and pilot wave and the retrocausal models, are fully compatible with a fixed four-dimensional reality, and some even seem to require it. The block universe is therefore neither confirmed nor refuted by quantum mechanics. It survives under some readings and struggles under others. What we can say is that the simple story, the idea that quantum randomness straightforwardly disproves the block, is far too quick. The deepest theory we have about the small-scale workings of nature leaves the door to the block universe open, even as it complicates the picture considerably. And that complication forces us to confront the central mystery directly. Does the act of observation create reality in the moment, or does it merely reveal what was already, in some sense, there? The question of whether observation creates reality, or merely reveals it, sits at the precise point where the block universe either stands or falls, and it deserves the most careful examination we can give it, because the stakes could hardly be higher. If observation creates reality, if the outcome of a measurement comes into being only when the measurement is made, then the future is not fully real in advance, and the block universe of relativity must be at least incomplete. If, on the other hand, observation merely reveals an outcome that was already determined, already a feature of the structure, then the block universe survives, and our sense that we are bringing the future into being as we go is another illusion to add to the flow of time itself. Everything turns on which of these is true, and the difficulty is that the experimental facts, remarkable as they are, do not by themselves decide the matter. Let us look closely at what the experiments actually show, because they are genuinely instructive even though they do not settle the interpretation. We have already met the double-slit experiment, in which an electron behaves as though it travels both paths at once. producing an interference pattern unless we measure which path it takes, in which case the interference vanishes and the electron behaves as though it went one way or the other. The natural first reading is that measurement disturbs the electron, knocking it out of its wave-like behavior, but a more refined class of experiments shows that the story cannot be so simple, and these experiments push the puzzle into territory that bears directly on the nature of time. They are called delayed choice experiments, and they were first proposed by the physicist John Wheeler, who understood their implications with unusual depth. The idea behind a delayed choice experiment is to wait until after the electron has presumably passed through the slits before deciding whether to measure which path it took. If the electron must commit to being either a wave passing through both slits or a particle passing through one, common sense says it must make that commitment when it reaches the slits. So if we delay our decision about what to measure until the electron is already past the slits and nearly at the screen, the electron should already have committed, and our late choice should make no difference. But that is not what happens. In these experiments, the electron's behavior matches whatever choice we make, even when that choice is made after the electron has supposedly already passed the slits. If we choose, at the last instant, to look for which path information, the electron behaves as though it went through one slit. If we choose, at the last instant, to detect the interference, the electron behaves as though it went through both. Our present choice appears to determine what the electron did in the past. Wheeler extended this idea to a cosmic scale to make its strangeness vivid. Imagine light from a distant quasar, billions of light years away, that passes by a massive galaxy on its way to us. The galaxy's gravity bends the light, so that it can reach us by two different paths around either side of the galaxy, an arrangement that actually occurs in nature and is called gravitational lensing. Now, here on Earth, we can choose how to observe this ancient light. We can set up our apparatus to detect which path the light took around the galaxy, or we can set it up to combine the two paths and detect interference. According to the logic of the delayed choice experiment, our choice today, billions of years after the light passed the galaxy, appears to determine whether that light travelled one path or both. A decision made now seems to reach back across billions of years and shape what happened in the deep past. It is tempting to leap from these experiments to the conclusion that observation literally creates the past, that consciousness reaches back in time and brings prior events into being. But this leap, exciting as it sounds, is not warranted by the physics, and seeing why is essential to understanding the real situation. The experiments do not show that the present creates the past. What they show is more subtle and in a way more profound. They show that it is a mistake to think of the electron as having a definite history, a definite path, before the full experiment, including the final measurement, is complete. The electron does not secretly travel one path or both paths, and then wait for us to find out. Rather, there is no fact about the path until the entire experimental arrangement, end to end, has played out. The past of the electron is not settled and then revealed, nor is it created after the fact. It is simply not a determinate matter on its own, independent of the whole. This is where the block universe offers a strikingly natural reading of these baffling results, one that dissolves much of the apparent paradox. In the block, the entire experiment exists as a single four-dimensional structure. The emission of the light, its passage around the galaxy, the setting of the apparatus, the final detection, all of these are events laid out together in the block, all equally real, all part of one connected whole. From this perspective, there is no mystery about the choice reaching back in time, because there is no flow of time for it to reach back through. The early events and the late events simply coexist, and they are correlated with one another as features of a single consistent structure. The path of the light and the choice of measurement are not cause and delayed effect across a flowing present. They are mutually consistent parts of one fixed four-dimensional pattern. The block does not require that the past be settled before the future, because in the block, past and future are settled together, as a unit. Seen this way, the delayed choice experiments, which seem so paradoxical when you insist on a flowing present and a fixed past, become almost expected in a block universe. Of course, the final measurement is correlated with the earlier path, because both are parts of a single structure that must be internally consistent. There is no need for backward causation, no need for the present to create the past, no need for consciousness to reach across time. There is only a four-dimensional pattern in which all the events fit together coherently, including the events we call the choice and the events we call the path. The strangeness arises entirely from trying to narrate the experiment as a story unfolding in time, with the electron making decisions as the present moment sweeps along. Drop the assumption of a flowing present, adopt the view of the whole block at once, and the tension largely dissolves. This is one of the genuine attractions of the block universe. It takes some of the most perplexing results in all of physics, results that seem to involve the future affecting the past or observation creating reality, and renders them coherent by removing the assumption that generates the paradox in the first place, the assumption that time flows and the present is special. And yet we must be scrupulously honest here, because the block universe does not actually answer the deepest question. It reframes it. It tells us that the events are all laid out together and mutually consistent, but it does not tell us why the particular pattern in the block is the one that exists rather than some other. It does not explain why this measurement yielded this result rather than another. It relocates the randomness rather than eliminating it, unless one adopts a specific interpretation like many worlds, in which every result occurs in some branch and the question of why this one shifts into the question of which branch you happen to occupy. So we are left in a position of real subtlety, and it is worth stating plainly rather than papering over. The experiments tell us with great reliability that quantum systems do not possess definite classical histories independent of the full context of measurement. The block universe offers a coherent framework for accommodating this, by treating all events as coexisting features of a consistent four-dimensional structure. But neither the experiments nor the block universe tell us, on their own, whether the specific contents of the structure were determined by something, or are simply brute facts, or are selected by a branching that realizes all possibilities. The question of whether observation creates or reveals turns out to depend, once again, on which interpretation of quantum mechanics is correct, and that question remains open. What the block universe does establish is that the apparent creation of reality by observation, the apparent reaching of the present into the past, need not be taken at face value. There is a consistent way to understand these results, in which nothing is created and nothing is reached back to, in which everything simply is, arranged in a pattern that holds together across all of time. But this coherent picture comes at a price that many find difficult to pay, and the difficulty leads naturally to a rival model that tries to preserve some of what the block universe discards. If everything in the future is already laid out, already a feature of the structure, then in what sense is the future open? In what sense are the possibilities we deliberate over real possibilities, if only one of them is actually written into the block? The block universe purchases its elegance and its consistency by declaring the future as fixed as the past, and to many thinkers this seems to give up something essential, both about quantum reality and about our own experience of an open and undetermined future. Perhaps they suggest there is a middle path, a model in which the past is fixed and real, as the block insists, but the future remains genuinely open, not yet written, still being made. This is the growing block, and it represents one of the most serious attempts to keep the insights of relativity while restoring the openness of the future. The growing block universe begins from a simple and appealing intuition, one that tries to honour both the physics and our deepest sense of how reality works. The past, on this view, is fixed, real, and settled. Everything that has happened genuinely exists, laid out as a four-dimensional structure exactly as the standard block universe describes. But the future is different. The future does not yet exist. It is not a region of the block waiting to be reached. It is genuinely open, undetermined, not yet real. And the present moment is the growing edge of reality, the leading surface where new events are continually coming into being and being added to the fixed and accumulating past. Reality in this picture is like a structure under construction, with the completed portion representing the past and the present moment, representing the active edge where new layers are perpetually being laid down. The block grows. The appeal of this model is considerable, and it is worth appreciating before we examine its difficulties. It preserves the reality and fixity of the past, which fits our sense that what has happened cannot be changed, and that the past is fully determinate. It preserves the openness of the future, which fits our sense that the future is not yet settled, that our choices matter, that possibilities are real. And it gives the present moment a special objective status, which fits the overwhelming feeling that now is genuinely privileged, that this moment is where reality is actually happening. The growing block tries to capture the best of both worlds, the four-dimensional realism of relativity for the past, and the open, dynamic character of becoming for the future and present. It is, in many ways, the model that comes closest to ordinary experience while still taking physics seriously. This model also fits more comfortably with certain interpretations of quantum mechanics, which is part of its attraction for physicists rather than only philosophers. If the collapse of the wave function is a real physical process, as the Copenhagen interpretation holds, then the growing block offers a natural home for it. The future is a realm of genuine quantum possibility, a spread of potential outcomes not yet realized. The present is where those possibilities collapse into definite actuality, where the wave function resolves into a single result, and where that newly determined event is added to the fixed past. The growing edge of the block is precisely the place where quantum indeterminacy becomes classical fact, where the open future crystallizes into the settled past. On this view, the strangeness of quantum mechanics and the openness of the future are two aspects of the same process, the ongoing creation of reality at the present moment. For those who find the fully fixed block universe too rigid to accommodate genuine quantum chance, the growing block seems to offer a way forward. But the growing block faces a serious and well-known difficulty, and it comes from the very theory that motivated the block universe in the first place. The difficulty is relativity, and specifically the relativity of simultaneity that we examined earlier. The growing block requires an objective, universal present moment, a single global edge where the past ends and reality is currently being added. The whole model depends on there being a definite observer-independent fact about which events have already happened and become part of the fixed past, and which events have not yet happened and remain open. There must be a cosmic now, the same for everyone, marking the boundary of the growing block. And this is exactly what special relativity forbids. Recall what we established. Different observers, moving differently, slice space-time into different sets of simultaneous events. There is no privileged slicing, no objective fact about which distant events are happening at the same moment as you. Your now and the now of an observer moving relative to you are genuinely different, and neither is correct in any absolute sense. But the growing block demands precisely such a privileged now, a single objective present that constitutes the edge of reality everywhere at once. If simultaneity is relative, then there is no agreement about where the edge of the block is. For one observer, a given distant event has already happened and joined the fixed past. For another observer, moving differently, that same event has not yet happened and remains in the open future. The two observers disagree about whether the event is real, settled and existing, or merely possible and not yet brought into being. In a growing block, this disagreement is intolerable. An event cannot be both real and not yet real, both settled past and open future, depending on who is looking. Either it exists or it does not. This is a deep and damaging objection, and it cuts to the heart of the growing block program. The standard block universe does not face this problem, because in the standard block, all events simply exist whatever their temporal location, and there is no privileged edge whose position observers must agree upon. The relativity of simultaneity is no embarrassment to the standard block, because the standard block does not single out any moment as the universal present. Different slicings are just different ways of carving up a structure that exists in its entirety, regardless of how it is sliced. But the growing block lives or dies by the existence of an objective present, and relativity appears to deny it exactly that. The very feature that makes the growing block attractive, its privilege now, is the feature that relativity rules out. Defenders of the growing block have not simply conceded the point, and their responses are worth understanding, because they reveal how deep the disagreement runs and how it touches on the foundations of physics. Some have argued that there might, after all, be a preferred frame of reference, a privileged way of slicing space-time that defines the true present, even if relativity treats all frames as equivalent for the purposes of physical law. Interestingly, modern cosmology does provide a natural candidate for such a frame. The universe is filled with the cosmic microwave background, the faint afterglow of the Big Bang, and there is a particular state of motion in which this radiation looks uniform in all directions. This defines a cosmic rest frame, a frame in which the universe as a whole is, in a sense, at rest. One could propose that this cosmic frame defines the true present, the real slicing of the growing block, even though the laws of physics themselves do not single it out. This is an ingenious move, but it comes at a cost that many physicists are unwilling to pay. The principle that no frame of reference is privileged is one of the foundational pillars of relativity, confirmed by an enormous body of experiment. To restore a preferred frame, even one motivated by cosmology, is to suggest that this principle is not fundamental after all, that beneath the relativistic appearances there is a deeper layer of reality with an absolute present, hidden from our experiments because the relativistic effects conspire to conceal it. This is not logically impossible. There are serious physicists who pursue such ideas, but it represents a significant departure from the standard understanding of relativity, and it requires accepting that the equivalence of all frames, which has passed every test, is a kind of cosmic coincidence masking an underlying absolute structure. Most physicists regard this as too high a price, and prefer to keep relativity intact and accept the fully fixed block instead. There is a further, more subtle problem with the growing block, one that the philosopher who named it, C.D. Broad, and later critics have wrestled with, and it concerns the present moment itself. In the growing block, the present is the edge of reality, the most recent layer added. But consider any past moment. At the time it was present, it too was the edge of reality, the most recent layer. So how does any moment know whether it is the genuine present, the real growing edge, or merely a past moment that was once the edge but has since been buried under later layers? Every moment, from its own perspective, seems to have equal claim to being the present, because every moment was, at its own time, the leading edge of the growing block. This raises a perplexing question about what it even means to be the objective present in a structure where every layer was once the edge. The problem suggests that the notion of a privileged moving present may be incoherent even on its own terms, quite apart from the difficulties relativity raises. Where does this leave us? The growing block is a serious and thoughtful attempt to preserve the openness of the future while accepting the reality of the past, and it aligns naturally with interpretations of quantum mechanics that treat collapse as real and the future as genuinely undetermined. For these reasons, it retains thoughtful defenders, but it sits in deep tension with relativity, which denies the objective present the growing block requires, and it faces internal puzzles about the very nature of the present moment it invokes. The standard block universe, by contrast, is fully consistent with relativity and pays no such price, but it does so by accepting that the future is as fixed as the past, surrendering the openness that the growing block fights to preserve. The choice between them is not merely a matter of taste. It turns on questions that physics has not yet resolved about the correct interpretation of quantum mechanics, about whether a preferred cosmic frame has any deep significance, and about whether the present moment is a real feature of the world or a feature only of our experience of it. And that raises the natural question of whether any experiment could ever decide between these competing pictures of time, or whether the debate must remain forever beyond the reach of measurement. Whether any experiment could decide between these competing pictures of time is a question that deserves direct and honest treatment, because it determines whether we are doing physics or something closer to metaphysics. A scientific hypothesis, in the strictest sense, earns its standing by making predictions that observation can confirm or refute. If the block universe, and the growing block and the flowing present all predict exactly the same experimental results in every conceivable situation, then choosing among them is not a matter physics can settle. It becomes a matter of interpretation, of which picture hangs together most coherently and fits best with everything else we know, but not a matter that any measurement could resolve. So we must ask, with care, whether these views differ in anything observable, or whether they are different descriptions of the same predicted reality. The honest starting point is that, in their simplest forms, the standard block universe and the naive picture of a flowing present do not differ in any directly measurable prediction about the outcomes of experiments. Both accept relativity. Both accept the same equations governing how clocks behave and how events relate. The disagreement is about how to interpret that shared structure, about whether the four-dimensional whole is all equally real, or whether only a moving present is real. Two physicists, one believing in the block and one believing in the flow, would design the same experiments, predict the same results, and agree on every measurement. Their disagreement lives at a level beneath the predictions, in the interpretation of what the successful theory is telling us about the nature of reality. This is why some have argued that the block universe is not strictly a scientific hypothesis at all, but a philosophical reading of established science, a way of understanding relativity rather than an addition to it that could be independently tested. This is a fair point, and it must be granted. But it would be too quick to conclude that the question is entirely beyond the reach of evidence, because the situation is more interesting than a simple stalemate. The various positions are not all interpretively equivalent. Some of them make commitments that, while not yet tested, are in principle testable, and the difference often comes down to quantum mechanics rather than relativity. Recall that the standard block universe sits most comfortably with interpretations of quantum mechanics in which the future is fixed, such as many worlds, pilot wave theory, and the retrocausal models, while the growing block sits most comfortably with interpretations in which the wave function genuinely collapses and the future is open. And here is the important point. Different interpretations of quantum mechanics, though they agree on the standard predictions, are not always perfectly equivalent. In certain regimes, particularly where quantum mechanics meets gravity, or in proposed modifications of quantum theory, they can come apart and yield different predictions. If they do, then experiment could indirectly bear on the block universe debate by favouring one family of interpretations over another. Consider, for instance, the proposals that the collapse of the wave function is a real physical process governed by its own dynamics, sometimes called objective collapse theories. These theories modify the standard equations of quantum mechanics slightly, so that superpositions of large objects spontaneously collapse very quickly, while superpositions of tiny particles persist in agreement with experiment. Crucially, these are not merely interpretations. They make predictions that differ very slightly from standard quantum mechanics, and those differences are being actively searched for in laboratories. Experiments are pushing to create superpositions of larger and larger objects, looking for the point at which superposition might spontaneously break down. If objective collapse is real, it would support a picture in which the future is genuinely open, and the present has a special status, lending weight to something like the growing block. If, on the other hand, ever larger superpositions persist exactly as standard quantum mechanics predicts, with no sign of spontaneous collapse, that would weigh against objective collapse and in favour of interpretations compatible with the fixed block. These experiments are difficult and ongoing, but they show that the debate is not entirely sealed off from evidence. There is another avenue, even more speculative, that connects the structure of time to the deepest open problem in fundamental physics, the long-sought reconciliation of quantum mechanics with gravity. Relativity, which gives us the block, and quantum mechanics, which gives us indeterminacy, are both extraordinarily successful, but they are not yet unified into a single consistent theory. At the points where they must be combined, such as the interiors of black holes and the first instance of the universe, our current theories break down and give nonsensical answers. Many physicists believe that a successful theory of quantum gravity will require a radical rethinking of the nature of time, and some of the leading candidate theories suggest something remarkable. In certain approaches to quantum gravity, time does not appear as a fundamental feature of reality at all. Instead, the fundamental description of the universe is timeless, and what we experience as time, including its apparent flow, emerges as an approximate large-scale feature from a deeper timeless structure. This idea, that time is not fundamental but emergent, appears in several distinct approaches to quantum gravity, which lends it a certain weight even in the absence of a finished theory. In one well-known formulation, the central equation describing the quantum state of the entire universe contains no time variable whatsoever. The universe, described as a whole, simply is, in a single timeless quantum state, and the appearance of time and change emerges only when one part of the universe is considered in relation to another, with one subsystem effectively serving as a clock for the rest. If something like this is correct, it would represent a striking vindication of the spirit of the block universe, and indeed something even more radical. Not only would there be no flowing present, there would be no fundamental time dimension at all, only a timeless structure from which the appearance of time emerges as a kind of approximation, valid at the scales we inhabit but dissolving at the deepest level. The block would be not the final truth, but itself an emergent feature of something more fundamental and stranger still. We must be careful here, because these ideas about emergent and timeless physics, fascinating as they are, remain unproven and contested. There is no complete and confirmed theory of quantum gravity, and the various candidates disagree with one another on many points. The timelessness of the fundamental description is a feature of some approaches and not others, and even where it appears, its interpretation is debated. What we can say is that the deepest currents in theoretical physics are not flowing back toward a fundamental flowing present. If anything, they are flowing further away from it, toward pictures in which time is even less fundamental than the block universe already suggests, in which the very dimension along which the block extends is itself an emergent and approximate feature of a more basic timeless reality. The trend of fundamental physics across a century of development has been to demote time step by step from the absolute and universal status Newton gave it toward an increasingly derived and observer-dependent role. So the experimental situation is genuinely mixed, and it would be misleading to claim more certainty than exists. On one hand, the broad question of whether reality is a fixed block or a flowing present may not be directly decidable by experiment, because the leading pictures often share the same predictions about what we will observe. In that sense, the block universe is partly an interpretive stance, a way of understanding relativity, rather than a freestanding hypothesis with its own unique signature. On the other hand, the debate is not entirely insulated from evidence. The correct interpretation of quantum mechanics, which bears heavily on whether the future is open or fixed, may yet be constrained by experiments on collapse and on large superpositions, and the eventual theory of quantum gravity, when it arrives, is likely to have profound implications for the nature of time, quite possibly favouring a timeless or block-like foundation over a flowing one. The question is open, but it is not wholly beyond the reach of future evidence, and that is an important difference from a question that could never be tested at all. This leaves us in an unusual position, suspended between what physics has established and what it has not yet determined. The relativity of simultaneity is established beyond reasonable doubt, and it makes a universal flowing present very hard to sustain. The fixity of the block follows naturally from relativity if one declines to add a preferred frame by hand. Quantum mechanics complicates the picture, but does not clearly refute the block, and under several serious interpretations actively supports it. The deepest theories under development lean, if anything, toward time being emergent rather than fundamental, and yet our experience insists with undiminished force that time flows, that the present is real and special, that the future is open and waiting to be made. The physics points one way, experience points the other, and this brings us to perhaps the most important question of all, the one that any complete account must eventually face. If the block universe is correct, if time does not really flow, then why does it feel so powerfully as though it does? What is happening inside us that produces the vivid and unshakable sensation of passing time within a structure that does not pass at all? The sensation of time passing is so fundamental to consciousness that explaining it away as an illusion can seem almost absurd, and so the block universe owes us an account of why a timeless structure should give rise to such a vivid and universal experience of flow. This is not a peripheral question that can be waved aside. It is central, a theory that declares the flow of time unreal, but cannot explain why we so powerfully experience that flow has left its most important work undone. So we must turn from the physics of space-time to the physics and biology of the experiencing mind and ask what it is about a conscious creature embedded in the block that produces the feeling of a moving present. The answer, as far as we can construct one, lies in the nature of memory, perception, and the processing of information, all of which are themselves physical processes occurring within the block. Begin with a basic observation about how the brain handles time. The brain does not have direct access to an external flow of time. What it has is a continuous stream of information arriving through the senses, which it processes, organizes, and stores. At any given moment, the brain holds a particular configuration, a particular state, that includes records of what it treats as the past, in the form of memories, and sensory information it treats as the present, in the form of current perception. Crucially, the brain at any moment contains memories, but contains no records of the future. This asymmetry is built into the physical structure of the brain at every instant, and it is, as we saw earlier, a direct consequence of the entropy gradient, the arrow of time established by the low entropy past. The brain can store traces of lower entropy earlier states. It cannot store traces of higher entropy later states, because those traces would require information flowing backward against the entropy gradient, which the second law forbids. Now consider what this means for experience. Take any single moment along your world line, any single cross-section of you in the block. At that moment, your brain is in a particular state. That state includes memories of earlier moments and sensory impressions of the immediate surroundings. From the inside, from the perspective of that brain state, there is a clear sense of a present moment. The current perceptions, set against a remembered past, the stored memories, with no knowledge of the future. The brain at that moment naturally interprets its own configuration as being located at a particular present, with the past behind it and the future ahead and unknown. This is true of every moment along your world line. At each one, the corresponding brain state contains memories of the earlier moments and no knowledge of the later ones, and so each one experiences itself as the present, poised between a known past and an unknown future. Here is the key move in the block universe account of temporal experience, and it rewards careful thought. The flow of time on this view is not something that happens to the block. It is something that arises from the relationship between successive brain states, each of which experiences itself as the present. Consider the version of you reading these words a moment ago, and the version of you reading them now. The earlier version had certain memories. The later version has those same memories, plus the memory of the intervening moment. Each version, at its own location in the block, feels itself to be the present moment, freshly experiencing with the past behind it. There is no single moving spotlight of nowness travelling along your world line. Instead, there is a whole series of moments, each containing a brain state that takes itself to be the present, each containing memories of the earlier moments and none of the later ones. The sensation of flow is what this structure feels like from the inside, when you are one of those brain states embedded within it. An analogy may help, drawn from something static that nonetheless produces an impression of motion. Consider the individual frames of a film. Each frame is a still image, fixed and unchanging, frozen on the strip. There is no motion within any single frame. Yet when the frames are arranged in sequence and presented to a viewer, the result is a compelling experience of continuous movement. The motion is not in any frame. It emerges from the relationship between the frames, from their ordered succession, and the way the viewer's mind knits them together. The block universe proposes something structurally similar for the flow of time. Each moment is a fixed frame, a static cross-section of the four-dimensional structure. There is no flow within any single moment, but the moments are arranged in an ordered sequence along the time dimension, each containing memories of the previous ones, and a consciousness embedded in this sequence experiences the succession as flow. The flow is real as an experience, but it is not a feature of the structure. It is a feature of how the structure is traversed from within. This account has a notable strength. It explains not only why we experience flow, but why we experience it in one direction, and why the present always feels like the leading edge of our experience. Because each brain state contains memories of earlier states and not later ones, the direction of experienced flow always runs from remembered past toward unknown future, never the reverse. The asymmetry of memory, grounded in the entropy gradient, gives the experienced flow its direction. And because each moment's brain state has no access to later moments, each one feels like the frontier, the furthest point experience has reached, the live edge of the present. There is no need for an objective moving present to produce this feeling. The feeling arises naturally in any sequence of brain states arranged along an entropy gradient, each remembering its predecessors. The block universe does not deny the experience of flow. It locates the source of that experience in the structure of memory and the arrow of entropy rather than any actual movement of time. Yet we should not pretend this fully dissolves the mystery, because it does not. An intellectual honesty requires acknowledging what remains unexplained. The account explains why each brain state would represent itself as present, and why the sequence of such states would generate an impression of directional flow. But there is a residual puzzle that some philosophers consider the hardest part of the entire problem. Why is there a feeling of presentness at all? Why does experience come with this vivid quality of nowness, this sense of being live and actual, rather than being a mere static representation? A photograph of you contains information about you, but does not feel anything. A brain state contains information, and somehow is accompanied by experience. The question of why physical processes in the brain are accompanied by subjective experience at all is the famously difficult problem of consciousness, and the flow of time is entangled with it. The block universe can explain the structure of temporal experience, the ordering and direction, and the sense of a present, but the raw fact of experience itself, the fact that there is something it is like to be a brain state embedded in the block, lies beyond what the block universe alone can address. This is not a special failing of the block universe. It is the same hard problem of consciousness that confronts every physical theory of the mind, regardless of one's view of time. No current physical account explains why information processing is accompanied by inner experience. The block universe inherits this difficulty rather than creating it. What the block universe does accomplish is to show that the specifically temporal features of experience, the sense of flow, its direction, the feeling of a moving present, can be understood as arising from the static structure of memory-laden brain states arranged along an entropy gradient, without requiring any actual flow in the underlying reality. The flow of time joins a long list of features of experience that turn out, on examination, to be contributions of the mind rather than direct readings of an external reality, much as colour is a construction of the visual system rather than a raw property of light, and much as the solidity of objects is a construction overlaying what is mostly empty space. There is something both humbling and clarifying in this reframing. It suggests that our most immediate and certain-seeming experience, the passage of time itself, may be a kind of interface, a useful representation constructed by the brain rather than a transparent window onto the fundamental nature of things. This would not be the first time that careful inquiry revealed the world to be profoundly different from how it appears. The Earth appears flat and stationary. The Sun appears to move across the sky. Solid matter appears continuous when it is mostly empty space populated by particles. In each case, the appearance is not false exactly, but it is a representation suited to our scale and our needs, not a direct disclosure of the underlying reality. The block universe places the flow of time in this same category, as an appearance generated by our particular vantage point as conscious beings embedded within a structure, rather than a feature of the structure itself. And if our experience of time can mislead us so thoroughly about something so basic, it forces a final and unsettling question about ourselves. In a universe where every moment already exists and the future is as fixed as the past, what becomes of choice, of deliberation, of the sense that we author our own actions and that the future depends on what we decide to do? The question of free will in a block universe is where the abstract physics presses most directly on human life, because if every moment already exists and the future is as fixed as the past, then the choices we're about to make seem, in some sense, already made, already written into the structure. This is a deeply uncomfortable implication for most people, and it deserves to be examined carefully rather than either dismissed or accepted in a rush. We need to be precise about what the block universe actually implies for human agency, what it does not imply, and whether the threat it seems to pose to free will is as severe as it first appears. The issue turns out to be subtler than the stark initial impression suggests. Begin with what the block universe straightforwardly entails. If the future already exists as a fixed feature of the four-dimensional structure, then there is a definite fact already about what you will do tomorrow and next year and at every moment until the end of your world line. The events of your future are laid out in the block, settled and real. In this sense, the future is fixed. Whatever you will do, and that doing is already a feature of reality, not an open question awaiting resolution. This much follows directly from the block universe, and there is no softening it. The decisions you experience yourself as making freely, as you deliberate and weigh options and finally choose, correspond to events that are already present in the structure, already determined as facts about what happens along your world line. It is tempting to conclude from this that deliberation is pointless, that since the future is fixed, your choices make no difference, and you are merely a passenger watching a predetermined script unfold. But this conclusion, though emotionally natural, does not actually follow, and seeing why is crucial to understanding the real situation. The mistake lies in imagining that the future is fixed independently of your choices, as though the outcome were settled in advance regardless of what you decide, so that your deliberation is a kind of idle accompaniment to events that would happen anyway. That is not what the block universe says. The block universe says the future is fixed, but it is fixed, including your deliberations and choices as essential parts of the causal structure that produces it. Your choices are not bypassed by the fixity of the future. They are among the events that constitute it. Think carefully about what this means. Your decision tomorrow is an event in the block. The outcome that follows from that decision is also an event in the block, and the outcome follows from the decision. The deliberation you go through, the weighing of options, the reasoning, the final commitment, all of these are real events that genuinely lead to the actions that follow. If you had deliberated differently and chosen differently, the subsequent events would have been different too, because they depend on your choice. The future is fixed, but it is fixed as the outcome of a process that runs through your deliberation, not around it. Your choices are not irrelevant to what happens. They are precisely the means by which what happens comes about. The block does not contain your actions in spite of your choices. It contains them because of your choices. This is the same insight that arises in the older debate about determinism, which long predates relativity and the block universe, and it is worth connecting the two, because the block universe does not actually introduce a wholly new problem. Determinism is the thesis that the state of the universe at any moment, together with the laws of physics, fixes the state at all later moments. If determinism is true, then the future is determined by the past, and given the state of the world long ago, everything that happens, including everything you will ever do, was already fixed. Philosophers have debated for centuries whether free will is compatible with determinism, and the position known as compatibilism holds that it is. The compatibilist argues that free will, properly understood, does not require that your choices be undetermined or random. It requires only that your choices flow from your own reasons, your own desires, your own deliberation, without external compulsion. A choice is free, on this view, when it is your choice, arising from your character and reasoning, regardless of whether it was determined by prior causes. The block universe fits naturally with compatibilism, and the compatibilist resources developed over centuries apply almost directly to it. The fact that your choice is already a feature of the block does not mean it was forced on you from outside, or that it bypassed your reasoning. On the contrary, the choice is in the block precisely as the product of your reasoning. It is your deliberation, your weighing of options, that produces the choice that the block contains. The fixity of the future is not a chain that constrains you from outside. It is simply the fact that what you will decide is what you will decide, that there is already a truth about the outcome of a process that genuinely runs through your own mind. To say the choice is fixed is just to say that you will, in fact, make it. It does not say that you make it for no reason, or against your will, or that someone or something else makes it for you. There is a useful way to see that the fixity of the future is not, by itself, a threat to agency, and it comes from thinking about the past. We do not feel that the fixity of the past robs the people of the past of their free will. Julius Caesar's decision to cross the Rubicon is now a fixed and settled fact. It cannot be changed. And yet we do not conclude that Caesar therefore made no real choice, that his deliberation was idle, that he was a mere passenger. We understand that his choice was free in whatever sense choices are free, and that its now being a fixed fact does not retroactively drain it of agency. It was a genuine decision when he made it, and its being settled now is just the natural consequence of its having been made. The block universe asks us to see the future in the same light. Your future choices are fixed in the block exactly as your past choices are fixed, and the fixity is no more threatening to your freedom in the one case than in the other. The future is settled in the same way the past is settled, by the events, including the choices that constitute it. This reframing does real work, but we should not overstate its comfort, because there remains something genuinely challenging in the block universe picture that compatibilism does not entirely dispel. Even granting that your choices are real events that genuinely produce their outcomes, there is still the fact that there is no openness in the future, no branching set of genuine possibilities, only one of which will be realized. In the standard block, there is exactly one future, and it already exists. The sense most people have of free will includes not just that their choices are their own, but that the future is genuinely open, that more than one outcome is really possible, that the path not taken was a live alternative that could have been actualized. The block universe denies this stronger sense of openness. There is one future, and it is the one in the block. The alternatives you imagine as you deliberate are not other real futures waiting to possibly happen. They are merely possibilities you entertain in thought, only one of which corresponds to what actually lies ahead. This is where the interpretation of quantum mechanics returns to bear on the question, because it touches exactly this point about openness. If the many worlds interpretation is correct, then in a sense all the alternatives you deliberate over do happen, each in its own branch, and the structure contains every possible outcome of every choice. This does not restore openness in the usual sense, since every branch is equally fixed and real, but it changes the character of the picture. On the other hand, if an interpretation with genuine collapse is correct, and the growing block or something like it holds, then the future may be genuinely open after all, not yet written, and the stronger sense of free will, with real alternative possibilities, might survive. So even the question of free will, which seems purely philosophical, connects back to the unresolved physics of quantum mechanics and the structure of time. The degree to which the future is truly open is not something philosophy can settle on its own. It depends, in part, on facts about the physical world that we have not yet determined. What we can say is that the block universe does not reduce human beings to passive spectators of a script written elsewhere. Your deliberations are real, your choices genuinely produce their consequences, and you are the author of your actions in every sense that the actual causal structure of the world allows. What the block universe removes is not your agency, but a particular metaphysical picture of the future as a realm of open possibility hovering ahead of an advancing present. It replaces that picture with one in which your choices are woven into a structure that exists as a whole, real and effective at their own locations, producing the future not by selecting among open alternatives, but by being the very events through which the single actual future comes to be. Whether this should disturb you or not is itself something you will decide through a process of reflection that is, on this view, already a part of the structure and no less genuinely yours for being so. And this leads us toward the largest remaining questions, the ones that physics has not answered and perhaps cannot yet answer, about what all of this finally means and how much of it we can claim to know. What we can claim to know at the end of this investigation is best stated by separating carefully the parts of the picture that rest on firm, experimental ground from the parts that remain genuine speculation. Because the block universe is a layered structure of claims with very different degrees of support, and treating them all as equally certain would be a mistake in either direction. Some elements are as well established as anything in physics. Others are reasonable inferences that most physicists accept, but that go beyond what experiment strictly compels. And still others are open questions at the frontier of knowledge, where honest researchers disagree and where the final answer may be decades away, or may require physics we do not yet possess. Sorting these layers is the last and most important task, because it tells us how seriously to take the central claim that every moment of your life already exists. Start with what is solid, because the foundation is genuinely firm and should not be underestimated. Special relativity is among the most thoroughly tested theories in all of science. Time dilation is not a theoretical speculation, but a measured, repeatable fact. The clocks aboard satellites in the global positioning system run measurably faster than clocks on the ground, by an amount that precisely matches the predictions of relativity, and the entire system would fail within hours if these effects were not continuously corrected. Particles created in the upper atmosphere, which should decay long before reaching the ground, are routinely detected at the surface because their internal clocks run slow at high speed, extending their lives by exactly the factor relativity predicts. Atomic clocks flown around the world in aircraft return, showing slightly different elapsed times than identical clocks left behind, again in precise agreement with the theory. The relativity of simultaneity, time dilation, the unification of space and time into a single four-dimensional structure, all of this is established beyond reasonable doubt. The four-dimensional spacetime of Minkowski is not a speculative add-on. It is the confirmed framework within which modern physics operates. From this firm foundation, the block universe follows with considerable force, though here we move from established fact to strong inference. The relativity of simultaneity, which is experimentally confirmed, means there is no universal present moment shared across the cosmos. Different observers genuinely disagree about which distant events are happening now, and no observer is privileged. This makes the idea of a single objective present, advancing uniformly through the universe, very difficult to sustain. If there is no universal now, then the most natural reading of relativity is that all events, whatever their temporal location, exist on equal footing, which is precisely the block universe. This inference is not strictly forced. One could, as we saw, try to add a preferred frame by hand, restoring an absolute present hidden beneath the relativistic appearances. But this requires abandoning the principle that no frame is privileged, a principle deeply woven into the success of relativity, and most physicists regard the price as too high. The block universe is the conclusion you reach if you take relativity at face value and decline to add unobserved structure to rescue the flowing present. It is a strong and well-motivated inference, even if it is an inference rather than a direct measurement. Beyond this, we enter the territory of genuine open questions, where confidence must drop and humility must rise. The relationship between the block universe and quantum mechanics is unresolved. Whether the future is truly fixed or genuinely open depends on the correct interpretation of quantum theory, and that interpretation is not known. Several serious interpretations are compatible with the fixed block, and some actively support it, but at least one major family of interpretations, those involving real wave function collapse, points toward an open future and something more like the growing block. Experiments on the boundaries of quantum mechanics, probing whether large objects can be held in superposition and whether collapse is a real physical process, may eventually constrain these options, but they have not done so yet. The question of whether observation reveals a pre-existing reality or participates in bringing it about remains, after a century of debate, without a settled answer. The deepest layer of all concerns the nature of time at the foundations of physics, and here we are frankly at the edge of human knowledge. The reconciliation of relativity and quantum mechanics into a single theory of quantum gravity is the great unfinished project of fundamental physics, and its implications for time are profound but uncertain. Some leading approaches suggest that time is not fundamental at all, that the deepest description of reality is timeless, and that time, including the very dimension along which the block extends, emerges as an approximate feature from a more basic timeless structure. If this is correct, the block universe is not the final truth, but an emergent description, accurate at the scales we inhabit but dissolving into something stranger at the foundation. Other approaches retain time as fundamental. There is at present no way to decide between them, because there is no complete and confirmed theory of quantum gravity. The nature of time at the deepest level remains genuinely unknown, an open frontier rather than a settled landscape. So when we ask whether every moment of your life already exists, the honest answer has several parts, and giving only one of them would misrepresent the state of knowledge. If relativity is taken at face value, and most physicists do take it that way, then yes, in the sense relativity implies, the events of your future are as real as the events of your past, all part of a four-dimensional structure that simply is. This is the natural reading of our best confirmed theory of space and time, and it is supported by everything we have measured about the relativity of simultaneity and the unification of space-time. But this conclusion carries genuine uncertainties that intellectual honesty requires us to keep in view. Quantum mechanics may complicate or qualify it, depending on an interpretation we do not yet have in hand, and the deeper theory of quantum gravity, when it arrives, may reframe the entire question, possibly dissolving time even more thoroughly than the block universe does, possibly restoring some feature of it we have not anticipated. The block universe is the best current reading of established physics, held with appropriate confidence in its foundations and appropriate humility about its frontiers. What makes this picture so compelling, despite its uncertainties, is how much it explains and how coherently the pieces fit together. It takes the confirmed structure of relativity and follows it honestly to its conclusion. It accommodates the otherwise baffling results of delayed choice experiments by removing the assumption of a flowing present that makes them paradoxical. It explains the arrow of time through the entropy gradient rather than through any mysterious flow. It accounts for our vivid experience of passing time as a construction of memory-laden brain states arranged along that gradient, each taking itself to be the present. It even finds room for a meaningful kind of human agency, with our choices woven into the structure as genuine causes of what follows. The block universe is not a collection of arbitrary claims, It is a unified picture in which the strangeness of modern physics and the texture of ordinary experience are brought into a single coherent account, even if that account leaves certain deep questions open. And perhaps that coherence, rather than any single decisive experiment, is the strongest reason to take the block universe seriously. It is what you get when you stop insisting that the universe must match our intuition of flowing time, and instead let the confirmed physics tell us what time is. The result is a reality stranger than our experience suggests, in which past and future are as real as the present, in which the flow we feel so certainly is a feature of how we're embedded in the structure rather than a feature of the structure itself, and in which the deepest nature of time may be stranger still than even this. It asks us to hold our most basic intuition about time more lightly, and to consider that the moment you're experiencing now, which feels so uniquely and exclusively real, may be just one location in a vast structure where every other moment is equally, permanently real as well. Whether the final physics confirms this picture, refines it, or replaces it with something we cannot yet imagine, the journey to this point has already revealed that time is far less simple and far more interesting than the steady forward flow we thought we knew. And the questions that remain open are not signs of failure but markers of a frontier. The places where our understanding of time runs out and the next discoveries wait, themselves already existing perhaps, somewhere ahead in the structure, waiting for us to arrive. We have now followed the block universe from its origins in the constancy of light through to the frontier where our current understanding gives out, and you might reasonably think the story is complete. But there is a dimension of this picture we have so far touched only lightly, and it concerns not the physics of the structure, but what it means to be a particular thing existing within it, a person persisting through time in a universe where time does not pass. This is worth dwelling on because it changes how the block universe feels, moving it from an abstract claim about the geometry of space-time to something that bears directly on what you are. Consider again the world line, the four-dimensional trace of your existence threading through the block from birth to death. We described it earlier as a long thin object stretched along the time direction, with the shape of your whole life frozen into the geometry. Let us take that description with full seriousness and ask what it implies about identity. In the ordinary way of thinking, you are a three-dimensional being who exists wholly at each moment and persists by enduring through time, the same complete object now as a moment ago, travelling forward through the present. The block universe suggests a different account. You're not wholly present at any single moment. The you of this instant is a single cross-section, a thin slice of a far larger four-dimensional entity. The complete you is the entire world line, the whole extended object, of which the present moment's version is only one part among many. This view has a name in philosophy. It is sometimes called perdurance, the idea that objects persist through time not by being wholly present at each moment, but by having different temporal parts at different moments, much as a long object extends through space by having different spatial parts at different places. A road does not exist wholly at each point along its length. It extends, with different segments at different locations, and the whole road is the sum of all those segments. The block universe suggests that you extend through time in an analogous way, with different temporal segments at different moments, and the whole you is the sum of all of them, the complete world line from beginning to end. The child you once were is not a previous version of you that has ceased to exist. It is an earlier temporal part of the same extended four-dimensional being that you are, as real and as present in the block as the part reading these words now. There is something striking in this, and it is worth letting it land fully. In the block universe, nothing that exists ever ceases to exist. The moments of your childhood are not gone. They are not erased or annihilated by the passage of time, because there is no passage of time to annihilate them. They remain fixed at their locations in the structure, permanently real. The version of you that laughed at some forgotten joke as a child, the version that felt some particular afternoon sunlight, the version reading these very words, every one of these exists eternally at its own place in the block. From the four-dimensional perspective, a human life is not a candle that flares and gutters and goes out. It is a permanent feature of reality, a shape woven into space-time that does not come into being and does not pass away but simply is, complete and entire, every moment of it equally real. This recasts even death in a particular light, though we must be careful and precise here rather than sentimental. Death, in the block universe, is the far temporal boundary of your world line, the event beyond which the world line does not extend, just as birth is the near boundary beyond which it does not extend in the other direction. The block universe does not promise any continuation beyond that boundary, and it would be dishonest to suggest otherwise. What it does say is that the boundary does not unmake what lies within it. The moments of a life that has ended are not destroyed by its ending, any more than the existence of an edge to a piece of fabric destroys the fabric within the edge. A life remains a real and permanent part of the structure, bounded but not erased. The events of that life happened, and in the block what happened is never undone, never converted to nothing. It holds its place in the four-dimensional whole, fixed and indelible. Whether one finds this consoling or troubling is a personal matter, and the block universe does not insist on either response. Some find a kind of peace in the idea that the moments they value are permanent, that a cherished afternoon does not vanish into non-existence but remains forever real at its location in space-time, that the people they have lost are not annihilated but persist as fixed features of the structure, their world lines complete and indelible. Others find the fixity oppressive, preferring the open future and the genuine novelty that a flowing present seems to offer, and feeling that a universe where everything already exists drains life of its spontaneity and its possibility. The physics does not adjudicate between these reactions, it describes a structure. What that structure means to a being embedded within it is a question each person answers according to their own temperament and values, through a process of reflection that is itself, of course, a feature of the structure. It is worth pausing to notice how far this carries us from where we began, and how strange the journey has been. We started with the most ordinary observation imaginable, that time seems to pass, that the coffee cools and the seasons turn. We followed a single stubborn fact, the constancy of the speed of light, through the work of Einstein and Minkowski into the unification of space and time. We found that this unification, taken seriously, dissolves the universal present and points toward a reality in which all moments coexist. We watched this picture survive its encounter with quantum mechanics, complicated but not destroyed, and we saw it offer elegant readings of experiments that otherwise seemed to defy sense. We traced the arrow of time to the gradient of entropy rather than to any flow, and we located the felt passage of time in the structure of memory rather than in the structure of space-time. And now we arrive at a view of ourselves as four-dimensional beings, extended through time, every moment of our lives permanently real. This is the reach of an idea that began as a technical consequence of two modest postulates about light and the laws of physics. It is a reminder of something important about science itself, that following confirmed principles honestly, without flinching when they lead somewhere uncomfortable, can transform our understanding of the most basic features of existence. The block universe was not adopted because it was appealing. For most people it is not appealing. It was arrived at because it is where the physics leads, when the physics is taken seriously, and that is precisely what gives it its weight. It is not a story chosen to comfort or to thrill. It is a conclusion reached by careful reasoning from established fact, and it stands or falls on that reasoning rather than on how it makes us feel. And yet, for all its reach, the block universe remains, as we have been careful to insist, a reading rather than a proof, a strong inference from our best current theories rather than a final and certain truth. The history of physics is a history of pictures that seemed complete, and were later revealed to be approximations of something deeper. Newton's absolute time seemed unquestionable for 2 centuries before relativity dissolved it. It would be a strange arrogance to assume that our current understanding is the last word, that no future discovery will reframe the nature of time as profoundly as relativity did. The block universe is the best account we can give from where we now stand, with the knowledge we now have. It may be confirmed and deepened by the physics to come. It may be transformed beyond recognition. What seems unlikely, given everything we have seen, is a simple return to the flowing present of common sense. The universal now ticking forward identically everywhere. That picture has been weighed against the evidence and found wanting, and whatever replaces or refines the block universe is likely to depart from it further still, not to restore the comfortable intuition we started with. So we are left, finally, holding two things at once, and learning to hold them together is perhaps the truest result of the whole inquiry. On one side, there is the immediate and undeniable experience of living in time, of this moment happening now, of a past remembered and a future anticipated, of choices weighed and made. On the other side, there is the structure that our best physics describes, in which all moments coexist, the present is not privileged, and the flow we feel so surely is a feature of our embedding rather than of reality itself. These two need not be reconciled by discarding either. The experience is real as experience, and the structure is real as structure, and the relationship between them, how a timeless four-dimensional reality gives rise to beings who feel time flowing, is itself one of the open questions at the frontier. The block universe does not ask you to stop feeling time pass. It asks you to consider that the feeling, vivid and certain as it is, may be the view from inside a structure that does not pass at all. A structure in which this moment, and every moment you have lived or will live, exists permanently, waiting at its own location, as real as the words in front of you now. There is one further thread worth following before we close, because it returns us from the grand sweep of cosmology and identity to something more immediate, the practical and conceptual tools that physicists actually use to reason about the block, and what those tools reveal about the constraints the structure places on itself. We have spoken of the block as if all its events were laid out with complete freedom, but this is not quite right. The block is not an arbitrary collection of moments. It is a tightly constrained structure, and the constraints come from the same place the whole picture came from, the finite speed of light. Understanding these constraints reveals that the block universe, far from being a loose and permissive idea, is a precise and disciplined one, with a definite internal architecture that determines what can relate to what. The central tool here is the concept of the light cone, and it is worth building up carefully because it governs the entire causal structure of the block. Return to any single event in spacetime, any point with its definite location and time. Now ask which other events that point can influence, and which other events can influence it. Because no signal, no influence, no causal effect can travel faster than light, the answer is sharply limited. From any event, an influence can spread outward in space as time advances, but only as fast as light can carry it. If you imagine light spreading out in all directions from an event, it traces out an expanding sphere growing larger as time passes. Plotted in space-time with time as one direction, this expanding sphere of light forms a cone, opening upward toward the future. This is the future-like cone of the event, and it contains every other event that the original event could possibly influence. Anything outside this cone is too far away in space to be reached, even by light, in the time available, and so it lies beyond all possible influence from that event. There is a corresponding cone opening in the other direction, toward the past. The past-like cone of an event contains every event that could possibly have influenced it, every event from which a signal travelling at or below light speed could have reached it. Anything outside the past-like cone could not have affected the event, because no influence from it could have arrived in time. So every event in the block sits at the junction of two cones, a past cone containing all its possible causes, and a future cone containing all its possible effects. Together these cones divide the entire block, from the perspective of that event, into regions with sharply different relationships to it. The interior of the future cone is the event's possible future, the events it might affect. The interior of the past cone is its possible past, the events that might have affected it. And the vast region outside both cones is something with no counterpart in everyday thinking, a set of events that can neither affect the event nor be affected by it, events that are causally disconnected from it entirely. This causally disconnected region is where the relativity of simultaneity lives, and recognizing this ties together threads we have been developing throughout. For events outside each other's light cones, there is no objective fact about which happens first. Different observers slicing the block differently will order them differently, and none is privileged, exactly as we found with the lightning strikes in the train. But for events inside each other's light cones, where one can influence the other, all observers agree on the order. The cause always precedes the effect, for everyone, regardless of motion. This is essential. If observers could disagree about the order of cause and effect, the block could contain contradictions, effects preceding their causes for some observers. The light cone structure prevents this. It guarantees that wherever causation is possible, The temporal order is absolute and agreed upon by all, while leaving the order ambiguous only for events that cannot affect one another, where ambiguity does no harm. The relativity of simultaneity and the absoluteness of causal order are not in conflict. They are two aspects of a single consistent structure, partitioned precisely by the light cones. This reveals something profound about the block universe that is easy to miss. The block is not a free arrangement of independent moments. It is a causally woven fabric in which the light cone structure threads every event to its possible causes and possible effects, and in which the order of causally connected events is fixed for all observers. The freedom that the relativity of simultaneity grants, the freedom of different observers to slice the block differently, is carefully limited to the regions where it cannot generate contradiction. The structure permits exactly as much observer dependence as is consistent with a coherent causal order, and no more. This is why the block universe can accommodate both the relativity of simultaneity, which seems to make time observer dependent, and the firm causal structure of physics, in which causes reliably produce effects in a fixed order. The two coexist because the light cones partition the block into regions where each applies. When gravity enters the picture, through Einstein's later and more comprehensive theory of general relativity, this structure becomes richer and more dramatic, though the essential idea survives. General relativity describes gravity not as a force, but as the curvature of space-time itself. Mass and energy bend the four-dimensional structure, and this curvature is what we experience as gravity. In the block universe, this means the block is not a flat, uniform structure, but a curved one, warped and rippled by the matter and energy within it. The light cones, which determine the causal structure, are tilted and distorted by this curvature. Near a very massive object, the cones tip and narrow, and at the most extreme, at the boundary of a black hole, the curvature becomes so severe that the light cones tip entirely inward, so that every possible future direction leads deeper into the hole and none leads back out. The block universe accommodates all of this. The curved space-time of general relativity is simply a block with a more intricate internal geometry, its causal threads bent by the matter it contains, but still a single four-dimensional structure laid out as a whole. General relativity also confirmed, with even greater authority, that the block universe is the natural reading of our physics, because it strengthened the unification of space and time rather than weakening it. The bending of light by gravity, predicted by general relativity and confirmed during a solar eclipse, the slowing of clocks in gravitational fields, measured precisely and corrected for in-satellite navigation, the existence of black holes, now observed in many ways including the detection of gravitational waves rippling through space-time. All of these confirm a picture in which space and time form a single dynamic structure that can curve, ripple, and warp. Gravitational waves are especially telling. They are ripples in the fabric of space-time itself, disturbances in the geometry of the block that spread outward from violent events like colliding black holes, and they have been directly detected stretching and squeezing space as they pass. You cannot have ripples in space-time unless space-time is a real structure capable of being rippled. The detection of gravitational waves is, in a sense, direct evidence that the four-dimensional fabric of the block universe is physically real, not merely a mathematical convenience. So the block universe is not only the natural reading of special relativity, it is reinforced by general relativity, by the curvature of space-time, by the observed bending of light and slowing of clocks in gravity, and by the direct detection of ripples in the space-time fabric itself. The structure has internal discipline, governed by the light cones that thread causation through it and fix the order of every cause and its effect. It can curve and warp and ripple while remaining a single coherent whole. Everything we learn about gravity, about black holes, about the large-scale shape of the cosmos, fits within this four-dimensional picture and deepens it. The evidence that space and time are aspects of one unified structure, rather than separate stages on which events unfold, has only grown stronger with every advance, and that unified structure, laid out as a whole, is the block universe. And this brings the investigation to its natural resting point, with the central idea seen now in full context, supported, constrained, and connected to the broadest sweep of modern physics. The block universe began as a consequence of light's constant speed, grew into a unification of space and time, survived the challenge of the quantum and the puzzle of the arrow of time, accounted for the felt flow of time and the structure of human identity, and revealed itself finally as a disciplined, causally woven, gravitationally curved four-dimensional fabric, confirmed in its foundations by everything we have measured. It remains an interpretation, a reading of the physics rather than a proven certainty, and the deepest questions about the nature of time await a theory of quantum gravity we do not yet possess, but it stands as the most coherent account we can give of what time is, drawn from our best and most thoroughly tested theories. Every moment of your life, on this account, already exists, fixed at its location in a structure that does not pass, and the present you feel so vividly is one slice of a far larger whole, real in its entirety, waiting at every point along its length, including the points you have not yet reached and the points you have already left behind, all of them equally and permanently there.